Here's the promised video of a PowerPoint on reading phase diagrams. So please work through this video at your own pace with a copy of the accompanying worksheet readily available. The goal of this is for you to become familiar with interpreting binary temperature composition phase diagrams and to recognize their key features and similarities. You can complete this video any time, but the material is examinable, so earlier completion leaves more time to ask questions and to integrate your understanding into the remaining lectures. Please pause the video when a question is posed so you can attempt it before revealing the answer. Questions are in Times New Roman font. Please post any questions on the discussion board. The phase diagrams, and especially surfactant phase diagrams, can look very complicated. They can be even quite overwhelming in the level of complexity of information that they contain. However, phase diagrams of very different surfactants do have a lot of common features. We want to try and recognize those first. They often have the same kinds of phases, and those phases have very similar structures. And at low temperatures, they crystallize into solids. And we'll look at this in more detail later. So take a look first at these two phase diagrams, one for an ionic surfactant and one for a non-ionic surfactant. They both contain a large liquid phase, a hexagonal phase, cubic phases, and a lamellar phase. There are regions of both phase diagrams that we'll just for the moment label as solids. Another different surfactant, another non-ionic surfactant, behaves in similar kind of ways with similar kinds of features. Liquid phase, hexagonal phase, cubic phase, and lamellar phase, and then a region below which there are solids present. A different, less water-soluble non-ionic surfactant, again, looks different at first impressions, but in fact is quite similar. There's a liquid phase, a couple of cubic phases, a lamellar phase. Notice that the horizontal axis, the composition axis on this particular surfactant, starts at 25% solution. So there's actually a phase not shown on this phase diagram at much lower concentrations where the surfactant is soluble, but we don't see that on this particular phase diagram. This phase here, called L3, is another liquid phase. It's generally known as a sponge phase, but its structure doesn't matter for what we're going to do today. Phase diagrams are maps of equilibrium compositions. They tell us how many phases are present at a given composition and temperature, composition shown on the horizontal axis and temperature on the vertical axis, and what those phases are, but they don't contain detailed information about structure. In a binary or two-component system at a fixed pressure, it's possible to make mixtures that form a single phase. They can be 100% pure crystalline surfactant. It could be 100% pure crystalline water or ice at a sufficiently low temperature, or any number of these phases that have variable composition, like a liquid phase called F in this phase diagram, or various liquid crystals. There can also be two coexisting phases, and a few of these are shown here. Ice plus cubic phase, crystal plus the phase just labelled M, for example. Or there can be three coexisting phases, although these can only exist in a binary mixture at a single temperature. Again, we'll come back to that a little bit later. Only a few of the illustrative two-phase and three-phase coexistences are shown on this particular phase diagram. This phase diagram, which you have a copy of on your worksheet, is the one that we're going to use as our reference for most of the rest of this video. Now, experimental phase diagrams are always incomplete. They represent phase boundaries as continuous lines, but they're based on a finite number of discrete data points, samples that have been made up at a particular composition and temperature, from which these boundaries are then interpolated. Now, thermodynamics defines for us the rules for how all phase diagrams must behave, not just surfactants. Now, single phases fall into two categories. They may have a fixed composition. This would include pure components like ice, pure crystalline water, like pure crystalline surfactant at 100% C12E6 on this axis, or compounds like hydrates. This particular surfactant forms a monohydrate labelled X.W and a dihydrate X.W2. Each of these exists at a single point along the composition axis. They're a compound on the phase diagram. Single phases can also exist over a range of compositions. Solutions are an example of this, shown as liquid in this phase diagram. The phase diagram doesn't tell us whether micelles or other self-assembled structures are present in a phase, only that they are a single thermodynamically stable phase above a melting point, below a boiling point, and between other kinds of phase boundaries. Structure may change within the composition. For example, there may be a sphere to cylinder transition with composition or with temperature. We just know that from the phase diagram that it's a single phase. Lyotropic liquid crystals, lamellar phases, cubic phases, hexagonal phases, and potentially others, also exist over a range of compositions as well as a range of temperatures. In the case of a liquid crystal, changing concentration, dilution of a liquid crystal, corresponds to increasing the spacing between the self-assembled structures. As we dilute the lamellar phase, the spacing between the bilayers increases. As we dilute the hexagonal phase, the spacing between the cylindrical micelles also increases. So now on the phase diagram on your worksheet, I want you to plot points at 30 weight percent, 50 weight percent, 75 weight percent, and 90 weight percent surfactant in water, all at 25 degrees C. When you've done that, identify how many phases are present at each of those points and what those phases are. So as you can see, all of those are single phases. At 30 weight percent, it's a liquid. At 50 weight percent, it's in the hexagonal phase, which is sometimes denoted with an E. At 75%, it's in the lamellar phase, which is sometimes denoted with a D. And then at 90 weight percent surfactant, it's in the liquid phase again. So, as I said before, 2 points within the liquid phase don't necessarily have anything like the same structure. They're just a single isotropic flowing liquid phase. Now, these lyotropic phases can also have melting points. There's a single point on the composition axis for which the phase is stable to the greatest possible temperature. You can warm it up to the maximum possible temperature. So on your phase diagram, mark the melting point of the hex phase on the phase diagram, and then write down its composition and its temperature. That's shown here. It exists at approximately 49 weight percent and a temperature of about 36 degrees. A bit hard to read with this scale exactly what that temperature is, but that's close enough. As with a pure phase, melting the surfactant to form the liquid, melting ice to form water, when we melt the hexagonal phase at that temperature, there are two coexisting phases, the hexagonal phase and the liquid phase. Warming it forms only the liquid phase, cooling it forms only the hexagonal phase. The lamellar phase also has a unique melting point, so does the cubic phase, but that one's difficult to see on this phase diagram. Now, phase diagrams are often compared to maps, but there's an important difference between a map, like a map of the world showing boundaries between countries or states, and a phase diagram. Phases can be separated by coexistence regions, and those coexistence regions may not have the same composition. So for example, on the worksheet on your phase diagram, I want you to plot points at 30 weight percent, 75 weight percent, and 95 weight percent, but at -4 degrees. Then identify what the two phases that coexist at each of those points are. So at 30 weight percent, it says 25 in the answer, 30 weight percent, at -4 degrees, the sample lies in the ice plus hexagonal phase, coexistence region. So ice plus hexagonal phase actually coexist. If we move across to 75 weight percent, the hexagonal phase and the dihydrate of the crystal coexist at -4 degrees. And if we go up to 95%, then the two phases that coexist are two crystals, the monohydrate and the dihydrate. Notice that at equilibrium, the whole sample must be at the same temperature, so the two coexisting phases must also be at the same temperature. Now, if we cool each of those samples down to -15 degrees, which phases coexist at that point? If we cool them down, then the 30 weight percent sample becomes ice plus the dihydrate. So does the 75 weight percent sample, and the 95 weight percent sample hasn't changed. The same two compounds coexist. We can use the phase boundaries to identify the compositions of the two coexisting phases in those two phase regions. They're determined by the endpoints of a horizontal line drawn through the sample, horizontal line reflecting the fact that they're at the same temperature. So ice plus hexagonal phase, for example, forms hexagonal phase with this composition, and ice with this composition, pure water. The amount of each phase will vary depending upon the starting composition along this line between those two phase boundaries. And you can calculate the amount of each of these using the lever rule, which you met, I think, back in lecture 16. Now, it's quite common actually for two phase regions in phase diagrams to be filled in with these horizontal tie lines, connecting the coexisting single phase compositions. So, for example, there would be tie lines connecting the ice with the hexagonal phase, the ice plus the dihydrate phase at low temperatures, the hexagonal phase plus the dihydrate, the lamellar phase plus the dihydrate, etc., etc. So we just draw in horizontal lines. It's not just colouring in or shading. The horizontal lines are there to show the coexisting phases are at the same temperature. These also exist between liquid and liquid crystal phases. For example, between the liquid and the hexagonal phase, the liquid and the lamellar phase, the lamellar and the liquid phase over here, cubic and lamellar, cubic and hexagonal, and between two immiscible liquid phases, which happen to form at high temperature. We'll come back to the origin of those later. Tie lines really clutter up phase diagrams. So they're not always drawn in, and you need to be able to recognize when you look at a phase diagram where the two phase coexistence regions with or without tie lines being drawn in. So on the phase diagram below and on your worksheet, I want you to identify which phases coexist at the points A to E shown. So for C12E2 in water versus temperature, you have points A, B, and C. And then for the C12E6 in water as a function of temperature, you have points D and E. Remember, the L1 phase, the dilute solution phase, is not shown on the C12E2 phase diagram because it only goes down to 25 weight percent surfactant. So we know that there's a more dilute phase, but we can't see the ends of those tie lines. So here are the phases that coexist. For A, L3 coexists with the dilute L1 phase. For B, L2 coexists with the L1 dilute phase, so again a liquid-liquid coexistence. For point C, this cubic phase, V2, coexists with a concentrated liquid phase, a liquid isotropic phase, as shown by these tie lines between V2, superscript 2 and L2. In the C12E6 phase, we have at point D coexistence between the liquid, the micellar solution, and the hexagonal phase. And at point E, we have coexistence between the cubic phase and the lamellar phase. Three-phase coexistence is next. The most common kind of three-phase coexistence is a eutectic. There are a couple of others, but you don't need to know about them yet. A eutectic is the composition at which a phase can be cooled to its lowest possible temperature before it separates into two phases. And at just that temperature, the intercooled phase and the two separate phases can coexist. You've actually seen these before in chemistry too. Surfactant phase diagrams can be confusing because they often contain many eutectics. So I think I found them all in this phase diagram, shown by these 1, 2, 3, 4, 5, 6, 7 red arrows. The high temperature phase for a eutectic is always a phase that can exist over a range of compositions. A solution, a liquid mixture, or a lyotropic phase. The low temperature phases can be crystals or solutions or lyotropic phases. They're very rarely solutions, so we'll focus just on crystals and lyotropic phases. So let's take a look first at one of the eutectics over here, which forms between the monohydrate and the pure crystal, and compare that with stuff that I think you've seen before in chemistry too. So here is a very generic diagram of two components, A and B, that mix in the liquid phase, called all melt in this diagram, but do not mix at all in their crystalline phase, so they form A plus B crystals. Let's map that onto our hydrates, so that instead of melt, we'll just call it liquid. Instead of crystals of A plus B, we'll call it X plus X dot W. And notice that the composition axis just runs from pure surfactant monohydrate, X dot W, up to pure surfactant X, and we won't worry about the temperature scale except that it's increasing. So the melting point of the pure surfactant is shown as TB. The melting point of X dot W, the monohydrate, is a little bit lower than that, shown at the end of this yellow region here. What happens if we cool samples in the liquid at different compositions? If I cool the surfactant on the right-hand side of point E, then that will cause pure surfactant to precipitate and be in equilibrium with the remaining liquid. If, however, we're at a lower concentration, we're closer to the monohydrate in composition, then cooling causes the monohydrate to precipitate instead, coexist in equilibrium with the remaining liquid. Of course, there's a point in between where if we cool down exactly at point E, we reach the lowest possible temperature where the liquid is stable. And when we cross that boundary, crystals of both pure surfactant and surfactant hydrate will precipitate. And if we're exactly at temperature Tc, which is the eutectic temperature, then the liquid will coexist with both of those kinds of crystals. Heating turns it back into a liquid, Cooling leaves crystals of only A plus B and no liquid. From that point of view, it looks like a melting point. It's a very abrupt transition, but it's not a melting point because two different crystals exist below the phase transition temperature, below the eutectic temperature, and a single mixed liquid exists above the phase transition temperature. If you want to look for more information on the generic features of these eutectics, you can use the link here. Crystalline solids don't have to be perfectly immiscible, as in the example I've just shown. A more general way of representing eutectics and these phase boundaries includes the possibility that a small amount of component A dissolves into the solid form of B to form what's called a solid solution. Here it's denoted beta. Equally, a small amount of B can dissolve into the crystal of A to make another solid solution, which here is denoted as the alpha phase. The features, and particularly the uniqueness of the eutectic composition and eutectic temperature, aren't affected by this. The eutectic point still looks and behaves the same way, but the coexisting phases that separate out are somewhat different. So solid solutions can take on a range of compositions, and in that sense, they're like lyotropic liquid crystals. So if I go back and look at some of our surfactant phases, and we compare the lamellar phase and the the surfactant dihydrate, and cool that through its eutectic temperature, that through its eutectic point here, then what we will see on the right-hand side is a pure crystal which can't dissolve any of the other component. So cooling a sample to the right-hand side of the eutectic point precipitates out dihydrate of surfactant in equilibrium with the liquid until the eutectic temperature is crossed, and then the second phase separates. But if we cool at a lower concentration, if we cool from the liquid through the two-phase region into the lamellar phase, through the two-phase region into the lamellar phase, which I've still just called alpha, then we see this solid solution-like behavior on the left-hand side. So this phase diagram on the left maps to the lamellar phase plus dihydrate region of our much more complex phase diagram for the surfactant. If we continue to cool down through the next part of the phase boundary, we would eventually go into a two-phase region where lamellar phase coexisted with the hydrate. But there's a finite temperature range where the lamellar phase exists on its own. So on the phase diagram on your worksheet, I want you to identify which three phases coexist at the eutectic formed when the lamellar phase is cooled at just the composition that gets you to its lowest possible temperature. Which two of those phases continue to be stable on further cooling, and then what happens when you cool it down even further? If we cool through the eutectic point of the lamellar phase, then it will separate into cubic phase at lower concentrations and the dihydrate at higher concentrations. So the three coexisting phases are cubic, lamellar, and dihydrate. If I cool it further, the lamellar phase is no longer stable, cubic phase plus dihydrate exist. If I cool it all the way down to minus 15 degrees, then we're back where we started some time ago, and the coexisting phases are pure ice and the dihydrate. What happens at intermediate temperatures? Well, there's a range of intermediate temperatures at which the hexagonal phase and the dihydrate coexist. So we'll see that second type of two-phase coexistence occurring again at intermediate temperatures. Let's see how good you are at identifying three-phase coexistence. So on the phase diagram on your worksheet, please mark the points where the following three-phase coexistences occur: ice, liquid, hexagonal phase, ice, hexagonal phase and surfactant dihydrate, and liquid, hexagonal phase and cubic phase. Okay, I hope you found them. This one is very shallow, but it's where hexagonal phase and ice coexist with the liquid phase. This one shows the liquid phase, hexagonal phase and cubic phase. On heating it becomes a liquid, on cooling it separates into hexagonal plus cubic. And the lowest temperature one, cooling the hexagonal phase down, it will separate into ice plus the dihydrate. So at just the eutectic temperature, those three phases coexist. So now let's come back and take a look at the low temperature solids notation that we saw when we first looked at phase diagrams. So for these three phase diagrams from one of the first slides, you will probably notice now that the regions just labeled solid actually describe lots and lots of different possible solids, including ice, solid surfactant, and possibly lots of surfactant hydrates, but also 2 and 3 phase coexistences. Once one or more solids precipitates out, it's very tedious to actually separate them and identify the phase boundaries. So often people don't go to the bother of doing that because they're interested in what happens when there's no solid present. In practice, this means that a lot of phase diagrams are very incomplete in the low temperature regions. So for dodecyl trimethylammonium chloride, we've got a reasonable amount of detail. For C16EO12, we have virtually no detail. And for the dodecynyl methyl glucamine, we have some intermediate level of detail. Compare the level of detail that's provided for the dodecyl trimethylammonium chloride and what we've labeled just as solids here with the high level of detail in terms of coexistence and hydrates available for C12E6. For the same level of resolution, we just draw in this orangey brown line showing what the solid was and label all of that solids if we were mostly interested in what happens at higher temperatures. The next step is to consider liquid-liquid immiscibility. So it's quite common actually for liquids to mix at high temperatures, but then only be partially miscible or completely immiscible at low temperatures. The basic reason for this is that if you go to high enough temperature, then the entropy of mixing eventually wins out over any intermolecular forces that may not favour mixing of the two components. Regular solution theory is the most common way to describe this behaviour, and you've seen a version of that for polymer solutions and polymer blends. The version of regular solution theory that's used for those systems is called Florey-Huggins theory. So let's take a look at a simple mixture of phenol and water. Phenol and water are miscible in all proportions above 66.8 degrees, but at lower temperatures they will separate into two components. The highest temperature where two liquid phases coexist is called the upper critical solution temperature, or UCST. And the phase diagram shown here tells you what the phase boundary between the single phase and two phase liquid-liquid coexistence looks like. If I take a 48% phenol water mixture and cool it down, it separates into two liquid layers when the temperature is below about 66 degrees, not quite at the maximum. So two liquid layers are formed, the less dense phenol's on top, the less dense water is on top, the more dense phenol is on the bottom. But neither liquid is pure phenol or water. The phase boundaries tell us the compositions. So if I cool this to 50 degrees, then the compositions of the two liquids are given by the ends of that tie line where they cross the phase boundary. So 11 weight% phenol, therefore 89 weight% water, and 63% phenol, 37 weight% water. Any other mixture at any intermediate composition that was cooled would separate into those two same compositions, but the amounts of each of the two phases would be different, and this again can be calculated using the lever rule. There's some more detail on the link given there. It's less common, but there are still quite a large number of liquid mixtures that are miscible at low temperature, but become immiscible on warming. This is due to complex temperature-dependent intermolecular forces. Eventually, when you go to high enough temperature, entropy of mixing wins out, and the two liquids will mix again as long as they're still in the liquid phase. Classic example of this is nicotine plus water, and it exhibits what's called closed-loop coexistence. Nicotine and water are miscible at low temperatures. When heated above 60.8 degrees, they separate into two phases, and upon continued heating up to 208 degrees, they will remix into a single phase, no matter what the composition is. Of course, at 208 degrees, the sample is under pressure, so this is not a constant pressure phase diagram, it's basically a constant volume phase diagram, which is just slightly different. The general point's the same though. So the lowest temperature where the two phases can coexist just before they mix into a single phase is called the lower critical solution temperature. So if I take a 48% nicotine water mixture, warm it up to 60.8 degrees, it will separate into two layers. Heating it to 120 degrees, those two layers will have the compositions determined by the ends of that tie line, where the tie line crosses the two phase boundaries, and then upon further warming they mix again to form a single solution. Now the reason for showing you this is because this behavior is actually quite common for certain types of non-ionic surfactants and certain types of amphiphilic block copolymers. The hydrophilic part is just slightly soluble in water if the hydrophilic part is non-ionic, and that can have some subtle temperature dependent behavior. So non-ionic surfactants of the CNEM type, as well as many block copolymer amphiphiles, have an LCST. In polymer and surfactant systems, we call this a cloud point. So upon warming, the clear micellar solution becomes cloudy before it separates into two layers. The concentration of surfactant in one layer is usually very low. It's sometimes represented as pure water, well, it's not really very pure. And then the other end is highly concentrated in surfactant. Now, LCSTs, or cloud points, are a common way in which people design and introduce what are called temperature responsive forms of soft matter, causing them to separate or to remix simply by triggering a change in temperature. And if you have a cloud point that's around body temperature, then you can use them in a range of biomedical applications. So, two-phase coexistence and composition. Let's just try and review a little bit. If we look at the phase diagram of C12E6 in water, there are generally three types of two-phase coexistence regions. There's liquid-liquid coexistence, there's crystals coexisting with something else, ice plus hexagonal phase, surfactant dihydrate plus lamellar phase, surfactant dihydrate plus surfactant monohydrate, for example. These tie lines are often very long, and the compositions of the coexisting phases are very different from one another. The third class is the mesophase coexistence curves. Lamellar plus cubic, cubic plus hexagonal, hexagonal plus solution. For soluble micelle forming surfactants, which are usually single-tailed surfactants, these tie lines are very short. That means the composition between the two coexisting phases is small. Often, the structures in the coexisting lyotropic liquid crystals or mesophases are also very similar to each other. For example, cylindrical micelles in the liquid align cylindrical micelles in the hexagonal phase. For these kinds of systems, it's actually pretty easy to make up a sample in a single phase region, a micellar solution, a hexagonal phase, a lamellar phase, or a cubic phase. But it's pretty hard to hit these two-phase regions between liquid and hexagonal phase and cubic phase. The composition difference between those two sides of the phase boundary may be less than 1 weight percent, in some cases less than 0.1 weight percent. This means that many phase diagrams do not report both ends of these coexistence lines very accurately. They often just show them as a single line. So it's important to remember that there's always a two-phase region present. So in C16EO12, in its phase diagram, we have the solids region, which includes hydrates, coexistence regions, and maybe eutectics, not very well mapped out. And then these single lines showing the boundaries that are actually coexistences between the liquid phase L1 and the cubic phase H1, between the liquid phase L1 and the hexagonal phase H1, between the cubic phase H1 and the hexagonal phase H1, etc., etc., etc. Each one of these boundaries is actually a coexistence region of a finite width, a finite composition difference. Okay? But often the data simply doesn't allow you to resolve that. The liquid-liquid miscibility gaps around above the cloud point, they're still pretty wide, so two-phase coexistence is normally shown for those, with or without tie lines. So on the phase diagram at left, which you have a copy of on your worksheet, please mark the cloud point of C16E12 in water, and then work out what are its composition and temperature. So the cloud point is here at this minimum. So it's at coordinates of around 92 degrees and somewhere below about 1 weight percent C16E12. Now again, for these low resolution phase diagrams with not a lot of data points used to construct the phase boundaries, it can be very difficult to identify exactly where the cloud point is, but it is at the minimum of that coexistence curve W plus L1. So there's a separate set of phase diagrams, or a separate looking set of phase diagrams, that comes about when we start to look at double-tailed surfactants, lipids, and other really hydrophobic surfactants. They look different, but they follow all the same rules. The primary reason for the difference is because the surfactant's not very soluble in water. That means it's not very good at forming spherical or cylindrical micelles in solution. It wants to form bilayers, and therefore it wants to form vesicles or a lamellar-phase. We have the same set of observations. There may be pure crystalline surfactant, there may be hydrates, monohydrates or dihydrates, or there may be ice formed when water is cooled below its freezing point. As before, they exist at a single composition on the x-axis, and they have a melting point like any other compound. If we take an example of dioctadeckyl dimethyl ammonium chloride, it doesn't make any micelles at all. What phases does it form? So on its phase diagram on your worksheet, identify all of the single phases formed by dioctadeckyl dimethyl ammonium chloride at different compositions in water. You should have been able to identify crystalline water, ice, the dilute aqueous solution called liquid, even though it only occurs at very, very low concentrations, the lamellar phase D, a high concentration phase also called liquid in this phase diagram, two hydrates, X.W2 and X.W, monohydrate and dihydrate, and two crystals. Turns out there are two different crystal forms for dioctadeckyl dimethyl ammonium chloride, a low temperature form X beta and a high temperature form X alpha. You might not have spotted those two as being different, or might not have been sure whether they were different from each other or not. Now if I take a 20% solution of dioctadeckyl dimethyl ammonium chloride, what phase or phases are formed in, at each of the temperatures 60 degrees C, 20 degrees C, and 10 degrees C. So take my 28% solution, plot a vertical line, and then look at those three temperatures. At 60 degrees, the dilute solution coexists with the lamellar phase. At 20 degrees C, the dilute solution coexists with the dihydrate, and at minus 10 degrees C, pure ice coexists with the dihydrate. We could draw tie lines in, horizontal lines in, to illustrate these coexistence regions, but it's not necessary and it would clutter up the phase diagram, as I said before. Now we can start to look at the relationship between the phase diagram and structure. Lamellar phase is a convenient way to do this. As compositions change throughout a lyotropic liquid crystal mesophase, so does the structure. In the lamellar phase, dilution from 90 weight percent surfactant in water to 70, 60, 50, 40, etc., adding water increases the separation between the bilayers, but the bilayer thickness remains essentially unchanged. So the relationship between despacing, composition, and bilayer thickness is given by the equation we've already seen in lectures. If the thickness of a dioctadecyl dimethyl ammonium chloride bilayer is 52 angstroms, and assuming, just to make the calculation a bit simpler, that water and the surfactant have the same density, so that weight percent and volume percent are equal to each other, what is the maximum possible bilayer spacing that can occur in the lamellar phase at 60 degrees C? Maximum spacing occurs at the highest possible dilution, and on this phase diagram that's close to 32 weight percent surfactant, or a volume fraction of 0.32, then using our equation, making D the subject, the repeat spacing is 160 angstroms. So we could go ahead and calculate a peak position for a diffraction pattern, for example. The next question is, what lamellar spacing would be observed in the lamellar phase of a sample that was prepared instead at 20 weight percent of surfactant in water at 60 degrees C? What happens when we go from 32% to 20 weight percent? At 20 weight percent, liquid and lamellar phase are coexisting, and the composition of the lamellar phase is given by the same composition as the maximum possible swelling of the lamellar phase, the location of this phase boundary. So the composition of the lamellar phase is also 32 weight percent. The spacing will also be 160 angstroms. All the additional water that was added to carry out that dilution did not in fact further dilute the lamellar phase. It just formed a separate liquid phase that's almost pure water. Very, very dilute solution of the surfactant in water, and it coexists with this maximum swelling lamellar phase. Okay, so we've been through a lot. When you've finished this and maybe gone back over it a couple of times and tried out all the questions in the worksheet, you should be able to look at a phase diagram and identify the single phase regions, as well as the two-phase coexistence and three-phase coexistence compositions or regions or temperatures. You should be able to distinguish between fixed composition phases and variable composition phases, solutions, mixtures, lyotropic phases. Lyotropic phases and mesophases are terms that are used interchangeably. Should be able to identify the melting point and eutectic points in any binary mixtures. Should be able to identify the upper critical solution temperature and lower critical solution temperature of cloud point, and recognize closed loop coexistence in liquid-liquid mixtures. Should be able to identify when there's missing information in phase diagrams, things like solids not showing complete coexistence and eutectic and hydrate information, and very narrow coexistence regions not being represented properly, being represented as a single line rather than two lines with a separated in composition. And you should be able to determine the compositions of the coexisting phases and relate these to mesophase structure. I don't need you to be able to apply the lever rule to work out the amount of each phase. You should be able to read off the compositions of the coexisting phases off the phase diagram though, and as we just did, relate those to mesophase structure. You may, reading this or reading further, notice that there are some other kinds of multi-phase coexistence called peritectics and polytectics. You don't need to know about those for these phase diagrams.